Hi, let's review OSPF today. When it comes to routing options, we really have two. Either we deploy a bunch of static routes or we use a routing protocol. OSPF particularly is considered a link state within the interior gateway protocol. As we may know, static routes can be easy to deploy but not easily to maintain. The more routes, the more subnets that we have in our environment, the more configuration that we need to push manually to all the routers and firewalls in our environment. When it comes to dynamic routing, a routing protocol is going to help us propagating and communicating that information, those additions, those removals, those changes across our network automatically. The IGP protocols like OSPF are commonly deployed within an organization versus an IGP, which are commonly deployed between organizations. And really, we have more protocols to choose when it comes to IGPs. For EGPs is really just BGP that we have there. A distance vector protocol do not have a complex way to determine the best path to a destination. It's usually just how far that destination is, versus a link state is going to create a tree of the environment, and with all that information it's going to calculate the best path to a particular destination. OSPF, as it is a link state, is going to create a tree of all the links participating in OSPF, all those connections, and try to map how the network looks. And with that information, it's going to help us visualize and calculate the best path, the best destination for each subnet. And OSPF particularly can be divided in multiple areas. It is mandatory to have area 0, the backbone area, but other areas can cascade from it. And depending on how we have that configuration, then the communication and the information exchange between areas and within either the backbone area, area 0, or the other ones is going to be different depending on how we set those values, which again is going to help us on how robust and how scalable OSPF can be. The OSPF network types that we can have in our environment, which will control some of the OSPF operation and messages, are this one, for example, point-to-point, the connection between just two routers, or broadcast, which is the most common one and the default on the Fortinet firewalls. It is going to use multicast, broadcast will, and is going to send communications to the multicast address 2224.00.5 for all routers to communicate their information, and 224.0.0.6 for a designated router. We're going to talk about a little bit of what a designated router is on a broadcast OSPF network. We also have point-to-point multi-point. It's not very common, but just important to know that this type of OSPF network does not support multicast. Before OSPF can start exchanging information between routers, a OSPF adjacency must be formed between those routers talking to each other. So the steps to create an adjacency are here on the slide. Keep those in mind. What are the different steps OSPF, the router, is going to go through before forming that adjacency? It is going to start with the init state as soon as we receive something back from a router, and that also is on our network trying to exchange information with OSPF. We're going to go to the two-way. We're going to the exchange star. We're going to exchange some data. Once we exchange that data, we are like synchronizing and loading that into our memory, into our OSPF process. We are going to loading state. Once that's done, we're finally fully adjacent and on the full state. But for that to happen, multiple elements must match between the routers participating in OSPF for that adjacency to actually work, and to establish all these elements must match. Area ID, for example, is, as we mentioned before, OSPF can be broken down in multiple areas, but the communication between those two elements, those two routers, they must match. They need to be in the same area for that adjacency to be formed. The area type, we can define what different areas for our OSPF connections. The regular one, then the default is just going to be the backbone, and all LSAs or link state advertisements are going to be allowed. We're going to talk about a little bit in a moment. Or maybe we can define a stub area or not so stubby area, the NSSAA. And this is just going to control how and what type of information or OSPF routers exchange within that area. That will be the area type that must match. Another element that must match will be the authentication. Like any other element out there, we need the right credentials to get access. So same here, if we don't have that matching, the adjacency won't be formed. The MTU on the interfaces communicating with OSPF must match as well. Another thing that must match is the network type. We mentioned before the area type is if it is going to be the backbone, if it is going to be a stub area, that will control what messages we're going to exchange for OSPF. For the network type that also needs to match are the ones that we mentioned earlier, like the broadcast, where a designated router is needed, or maybe the point-to-point, or the point-to-multipoint, where multicast is not supported, for example. That definition must match as well. The subnet that we have configured on that particular interface also needs to match. And finally, the timers on how OSPF is going to operate, those also needs to match. We have the hello, the dead, and the wait timer. The hello timer is just a simple, hey, are you there? Hey, are you there? And we're expecting to receive like, yes, I'm still here. Yes, I'm still here from the other OSPF speakers. The dead timer is how long are we going to wait without receiving those reply backs before consider that peer, that neighbor down and do the adjustments in our OSPF process. The wait timer is just how long a router is going to wait after it boots to try to scope the network, look around, ask some questions, just try to determine if it is on a broadcast network and if a designated router has been already elected. The OSPF, we can define for the OSPF process, we can define a router ID either manually or it is going to be automatically chosen from the highest IP already configured on a router. And this is going to help us to identify our router and also could be used as a tiebreaker if needed later on. Within our OSPF environment, we're going to have different type of routers depending on their role and position in our network. An internal router is where all the interface belong to the same area. A backbone router has at least one interface on the backbone area or area 0. An area border router or ABR is going to connect two or more areas together. But remember that all additional areas must connect to area 0. So we know that any area border router has at least one of their links on area 0. And finally, the Autonomous System Boundary Router, or ASBR for short, is going to be a router that is part of an OSPF process, but at the same time is part of a different routing protocol, maybe BGP, maybe RIP, and it is channeling all that information into our OSPF process. So over here we have a combination of different connections. We have point-to-point connections at the top and a broadcast network time at the bottom with 4 routers over there. As we've mentioned before, if we have a broadcast network, OSPF is going to elect a designated router and if possible, a backup designated router, and everything else is just going to be a DR other. And that's how OSPF is going to handle and help synchronizing the routing table, not a routing table, but the OSPF information within all those routers on the broadcast network. The designated router is going to be elected either by the highest priority that we could set, and if not, by the highest router ID. That's why it's helpful to define it manually versus just hoping for the highest IP, which also can change with time. But the designated router, once elected, all the other routers on the broadcast area are going to pass their information. Hey, this is all my subnets. Hey, this is all the information I have. The designated router is going to collect all that information and then push that out to the other routers so they can receive and have a one source of truth. Yeah, here we are just mentioning how the process, the election happens. The highest priority go first. If there's a tie, we go to the highest router ID. And if there is a tie there as well, then it's the highest interface IP. In this particular example that we have on the screen, the two at the top, although they had higher priority, are not part of a broadcast network type. Therefore, there's no need for them to be a DR. It's just a point-to-point, and we don't elect DR or backup designated routers on non-broadcast networks. So that leaves just the other routers, and the one right in the middle. It is going to be the designated router just based on the router ID, which is higher because the priority were tied. The other routers are just going to be DR other, and the remaining router is going to be the designated router, really. So once the designated router is defined, then we do the same process again to try to define a backup designated router for a broadcast network. And the designated router, the backup designated router is just going to do the same purpose, the same role, trying to collect all that information and distribute the OSPF combines synced information to the other routers if the designated routers happens to be unavailable. And yes, like we mentioned before, the others are just going to be the remaining routers on that broadcast network. All routers will create full adjacency with the designated router and the backup designated router, and there's not going to be full adjacency between their remaining ones. It will look something like that at the end. Everyone is going to have full adjacency towards the DR router, to the backup designated router as well, but between the DR others, they won't form an adjacency. It's not needed. All right, so we mentioned it a little bit earlier, but the link state advertisement, or the LSA, is how OSPF exchange information between the routers on our network. And this is going to contain the information about the links, the states, and the different ways to calculate and create the tree and create the metrics to determine the best path to a single destination. The first type is the LSI type 1, and these are generated by all the routers and describes its own information, and is going to be broadcasted to everybody else on that particular link. The type 2 is generated by the designated routers, and is going to describe their connections, the combination of everybody else's there. So the designated router received type 1 messages because all the other routers are just broadcasting what they have. The designated router will receive that, will collect that, will combine it, and then will push that information to all the other routers on their network. Then we have the summary LSAs. Those are type 3 and 4. And these are generated by an area border router. And as we can see on the slide, when we go from area 5 to area 0, the ABR is going to create that summary route, pushing that to area 0. If we happens to have that same situation there when we are going from area 0 to area 10, then again, that ABR is just going to be pushing a summary LSA to area 10, which is going to be a type 3 or 4. If we have ASBR, which is going to be collecting information from a different routing protocol and then dumping that into our OSPF environment, that's going to be type 5 LSA. We can see information, the LSA information that we are generating and exchanging on the router with the get router info OSPF database self-originate. Those are going to be actually not the ones we receive. So with the command get router info OSPF database self-originate, we're going to see different LSA type that the router is advertising over. So this is really interesting when we have a ABR or an ASBR. We will see that on the lab later on, but we'll see what type of LSAs those routers are pushing to our network. Very, very small command over here with a lot of information, but the get router info OSPF database router LSA is just going to give us more and more detail on all those LSAs that are being generated. And just for conclusion, let's remember that OSPF is a link state protocol. Is going to create a tree of our environment, and with all that information is going to calculate the best path to a particular destination. The OSPF adjacency is going to be formed between two routers before they can exchange OSPF information. But for that to happen, multiple elements must match for that agency to be formed, like the authentication, the MTU, the timers, and other elements must match for the adjacency to be formed so they can exchange OSPF information. The router types will define how what's the role of each router and what type of messages we're going to have in our environment, controlling what SLAs we're going to see. Like the type 1 is going to be generated by all routers, creating a description of what they own, what they have. The type 2 LSA is going to be pushed by the designated router to all other routers on that broadcast environment. The type 3 and 4 summary LSAs are going to be created by the area border router when the communication goes from one area to another one, versus the summary 5 LSAs going to be pushed by a ASBR when that information is coming from a different routing protocol. Thank you.